Okay, the screen is visible now. Whatever I am sharing.
Yes, sir.
Okay, you know this class actually, huh? So it's a compound semiconductor technology, correct? And you know this is actually kind of elective courses, so it's optional for you. That you please remember. So if you see your routine timetable, okay, you have a three choice. One is computer, compound semiconductor and technology. Okay, and second thing is actually photonic integrated circuit. And third one is actually, I think, digital VLSI. Will be taken by Shibarani ma'am. But that is most probably uh, by NPTEL or some other mode of online teaching. Okay, there won't be kind of one-to-one teaching over there. Okay, so you have a three optional or three elective courses. So you have to choose two. Okay. So that too, please remember. Okay, this course, compound semiconductor and technology, is part of this elective course, as I told you already. And this, as you know, that it is a continuation of physics of micro nano electronics devices. Okay, why it is a continuation? Because we have focused the last time only on silicon, a very basic rules of semiconductor, not rules regulation, not too much deep depth on it. Here we'll tackle another group of semiconductor called compound semiconductors. You may ask why? Why not silicon? Because if you see general things, so silicon is actually very common because your CMOS foundry, your mobile phone, your laptop, everything based on CMOS technology. And CMOS obviously dominated by silicon. Okay. The complementary metal oxide semiconductor, there is no other choice apart from silicon till now. But still, this course, we are actually focusing compound semiconductor. There are the two reasons. Main thing is that there are some strategic application, classified applications, where we cannot use silicon. Example, defense. Okay. So, you know, so defense application, if you say the classified applications, like there are few things there actually you need to apply compound semiconductor. Why? As an example, okay, we'll be talking about in this course HEMT. What is HEMT? HEMT is actually high electron mobility transistor. Okay. So introduction. So here actually I'm talking about what I'm telling about. So this HEMT structure, now what is the significance of HEMT? Modern days, if you want to have a very high speed application, it may be RF mixer, it may be adder, okay, multiplier, whatever. Like what do you mean by mixing? Okay, that means suppose communication application, high speed communication, where it is happening, right? So you have a proper modulation, and those things are happening, and at very high speed. So there people of device, HEMT, high electron mobility transistor. There's another variation is there called the MESFET, metal semiconductor field effect transistor. So there is another variation called the MESFET. So FET, you understand what is FET, field effect transistor, and MES means metal semiconductor transistor. Metal. So semiconductor. Field effect transistor. So this is also kind of classified application, very specific application people are using MESFET. Similarly, there is another group of, already, but still let me write. Schottky transistor. So you see that these are the specific high frequency devices are there. Okay, where you need, suppose you want to have a high frequency communication, or not high frequency, high speed communications, or high speed data processing, or detectors. There people are using at this three group of configuration. You may ask, what's about impact diode? What's about pin diode? What's about tunnel diode? So these are the variations are there. But these all three variations like impact diode, tunnel diode, pin diode, that also people are saying micro devices, okay? High speed devices, but still this kind of primitive age, old ages. Okay, because nowadays people are actually most cases, like if you see our defense applications or space applications, okay, or special application like where safety on other things are related, there people are using this kind of most reliable devices, Schottky, MESFET, HEMT. Why the reliable terms comes? Just I am giving you one example. You are using a mobile, okay, nowadays. Today you purchase the mobile, fantastic. And that, so before buying that mobile, what you do? Normally you read the specifications, like what is the speed, what if it is a Qualcomm processor, what is the speed, how the processors, okay? What is the camera, general features we read, right? All these things we read, RAM, everything. And based on that you buy. Now, you know the performance today. Now I'm just asking you, after 1 year, if you try to see this performance, you see it deteriorates. The performance is not the same the day when you purchase first time. Okay, so it deteriorates with time. That is actually very unacceptable when it comes with a reliability. Okay, when it comes very classified, a very precision application like satellite applications, like missile application, like submarine application, all these kinds of defense space application where you cannot have this type of luxury of deteriorating a particular performance. And there people are using all these things. There is a disadvantage, and that disadvantage is that whatever, like this HEMT, MESFET, and Schottky transistor is not a complementary in nature. What do you mean by complementary in nature? Yes, complementary in nature means you cannot make a CMOS out of this one, out of this configuration. I'll tell you in a minute why, but that is actually biggest disadvantage. We know the configuration of MOSFET, right? We know that configuration of MOSFET like metal semiconductor field effect transistor. And based on the MOSFET configuration, we make CMOS, okay? Like PMOS, NMOS, in such a manner that it will work as an inverter. But this configuration, this HEMT, MESFET, and Schottky transistor configuration is not actually really compatible with the CMOS configuration. Okay. So one of these reasons is that I am telling you at the moment, like if you see this kind of application, the main material is not silicon. The semiconductor is compound semiconductor, 3-5 semiconductor, 2-6 semiconductor, 4-4 semiconductor, like that. What is 3-5 semiconductor? Normally gallium nitride, gallium arsenide, indium arsenide, indium phosphate, this kind of material. Okay. And why it is like that? The single answer, single statement I'm giving today's class, that is the mobility of this compound semiconductor is way higher than silicon. For an example, the mobility of gallium arsenide is 8,500 centimeters per volt second, whereas silicon less than 1,000. So it is 8 times higher. Okay. So that means you are expecting our mobility is 8 times. So just for an example, like why we are seeing this part, look at what is the cutoff frequency. You know already, because you already come from a basic background. So what is the cutoff frequency? So your cutoff frequency is actually proportional to GM. Okay, your cutoff frequency. Okay. So now it looks like that if you have a mobility is high, so your cutoff frequency is also high, or operating whatever frequency is also high. Now if it is a GM, so GM, this transconductance is also proportional to mobility, right? If you can, just for an example like MOSFET, if you see MOSFET, what is I? I is equal to mu. Tell me. Can you tell me?
Half mu n COX WIL
Sorry.
half mu n COX WIL VGS minus VT ka whole square for
Okay.
saturation
That is in
region.
saturation region. Okay,
Yes, sir.
fine. Okay, so you have given me the answer actually. So like whatever current is flowing, so it is proportional to your mobility. That is fine, right? So I is proportional to mobility, so dV by di. Okay. So your GM, what is GM? What is GM?
DI by VGS.
Di by dVGS. Okay.
DVGS.
So that means your GM is also proportional to your mobility. Okay. So that means if your mobility high, your GM high, and if your GM high, so cutoff frequency is high. So that means if you push your cutoff frequency more or more higher range, your operational frequency also actually increasing. Okay. And to push take your GM higher and higher, you need one of these parameters is to increase the mobility. But mobility is actually kind of sole properties of a particular material, right? So silicon mobility is kind of fixed, which you cannot do much. Similarly, so that means you can reduce silicon mobility, but you cannot increase silicon mobility up to 1,000, more than 1,000. You cannot increase. Similarly, the compound semiconductor mobility is 8,500, okay, which is kind of 8 times higher or 9 times higher than silicon. So definitely it's a natural choice. So compound semiconductor is a natural choice here. There are other things also there, which I'll discuss later on. So that is one of the reasons that people for classified application, for high frequency application, for high frequency or high speed communication or detector. Why detector? This is also a fantastic thing that we are going to study. Suppose I'm taking you because last couple of years we are also our lab is also trying to develop a detector called a terahertz detector. What is terahertz detector? Terahertz detector is called the mysterious detector or forbidden detector. People see that people know that what is happening in terahertz region, we don't know. And terahertz, because people know about the IR detector, definitely you know, because all things what you are getting IR image only, whether satellite data or all these things. No? There is, so people already knew, and there is a fantastic image processing algorithm is there. People do plenty of things out of there. But after IR, people somehow stop. People interested to work on it, but people thinks that something is there in terahertz region, which is not good thing. Okay, and not a fantasy, because things are there. There are particular things are there which people are actually thinking about this region, and that's why this terahertz region people are not interested to work. But last 5 years or 6 years, people are thinking, okay, let's explore terahertz. Okay, let's explore what are the unknown radiations are coming in our earth, to our earth. What are the unknown radiation as evolving through Big Bang? What are the unknown radiations are actually generating for any planet? Can I get some information? Can I have another, like IR, infrared image processing is already established, but terahertz image processing is not at all established. So what is there? So now then onwards, people started thinking of a terahertz detector, and definitely people are working on it. There are multiple issues are there. One of these issue work in this field, in even the research laboratory itself, we don't have a proper terahertz source. Okay, forget about detector. We don't have a source, so how can we calibrate a detector? So that's another problem. People have started working both terahertz and detector. And good thing is that if you want to make a good terahertz detector, you have to believe on such kind of compound semiconductor technology, not silicon technology. There are few papers are there in silicon technology. You must build terahertz detector, but the problem is the noise margin is too high. Why high? We'll see after 10-15 lectures, not now. Okay. Another part is that the major problem of working in silicon is that it cannot work at low temperature. Now the question is, why we want to work on low temperature? That answer will be giving, I'll be giving after 10 lectures, not now. So compound semiconductor is that semiconductor device where you can work in low temperature. Question is why? Why you want to work in low temperature? Okay, I'm just giving, now remember classified application. Suppose you want to deploy a particular device in Antarctica. What you will do? Do you bring a silicon device? It won't work. You will work like you have to put a silicon, then you have to make a thermal jacket and you have to heat up the system so that silicon will get a particular temperature, and then the silicon will start working. At low temperature, it's called the freeze out condition, which you have studied last semester, like that below a cutoff zone, if you don't have a sufficient energy equivalent to 45 millielectron volt, because when you semiconductor, you are giving a zone, you are giving a layer, or you are generating a particular energy level, okay, 45 millielectron volt down to your conduction band, okay, and you have to give minimum 45 millielectron volt to pump electron from your donor level to your, you have started this thing. Now if your overall situation is such that the overall energy is down to 45 millielectron volt, no, your silicon won't work. But nice thing is that your compound semiconductor will work. Okay, so that is very classified application, because Antarctica, it's not like all people will do work on this. Okay, look at this part. Second thing is, suppose you want to dip a particular device down to suppose your device, you want to work Mariana Trench. You know Mariana Trench, right? You know Mariana Trench because it's the deepest point in the ocean. Okay, the temperature is also equally low, and you want to sense, you want to put lot of sensors over there. That is a major challenge in Mariana Trench. You don't have a proper sensor over there because most of the sensor is silicon based. So if you want to deploy a particular sensor over there, or even a drone, underwater drone over there, you need to have some sort of arrangement on this compound semiconductor. Look at the cryofield, cryogenic. There are fantastic research zones in their cryogenic research. You say that where is the application of cryogenic? Okay, out of space application, definitely it's a cryogenic. Yeah, if you want to deploy a sensor in moon, or Mars or whatever, there is a one zone is a relatively huge temperature, another zone is actually very low temperature, and there also you cannot work with silicon. You need to have another things. And compound semiconductor is a natural choice. Still there is some limitation, but we'll work on it. So what I'm saying that there is a classified application where you cannot have other choice than the compound semiconductor. Classified, very special application, and we have to work on it. Okay, and definitely this okay, number one, and definitely this subject, you understand, this compound semiconductor technology is a very special subject, and it's mainly research topic. Okay. Now, job perspective, if we see that part, that will come in a minute. Okay, but still I have to tell something. Power, because whatever I told is IR semiconductor, like a high-speed device. What's about the power semiconductor? Just Google it. Modern days power semiconductor. I have a lot of friends, Anindra Dajgupta, Rajivan, and all these things. So they are actually nowadays people are working the high power device, kilovolt range. They are thinking of, not thinking, they have started working on gallium nitride based device. Gallium nitride based HEMT, high electron mobility transistor. Silicon carbide based HEMT. High frequency, high power application, HEMT. You may think about how it is possible, high frequency, high power device. We'll see later on, because if you increase the frequency, power will drop down. Then bandwidth product will drop down. So all these things are there, because, but for power electronic device, if you want to have a high threshold voltage, you don't have any other choice. And here is actually ballpark or benchmark. One is classified application, what I already told. Now you see, now it is broadening. Another is power electronics, power device. And here the problem is you cannot use silicon. You have to use compound semiconductor. It has a plenty of applications. It's not a classified application, because in normal days people are coming up, because we are actually now, power is actually major factor. Like all the grid, all the power stations, to everything, like you have a transformer, a lot of things. Okay, like people needs a high power operation device, high power threshold device, and there you have only one choice, compound semiconductor. So it's not only the classified application, it's a more generate power application, but it is not coming, it is not useful directly to us. You can say like how a common man will use power semiconductor device. No, but you are not, common mans are not using power semiconductor device in randomly, but yes, they need it. Why they need it? Look at, you are traveling by train, you are traveling by flight. Look at that things, all actually high power device. Why high power device? Definitely you are handling huge power over there, because your train or your flight or your submarines are isolated from the power device. Like you don't have a particular power grid over there. So you are storing your power in your flight, okay, or you are generating your power. So it has to be high voltage power handling capability. Should have huge power, no? Lot of sensors inside the flight, engines are running, fantastic things are there. Two things, suppose a huge lightning, you are actually, you're driving your train in a thundering condition, okay? Lightnings are happening, right? So that means your all device should be capable of withstand that thundering or lightning. Okay, so all things actually power devices are very common man use. You can, okay, you go more. What are the more common man use lightnings are coming, which are dominated by compound semiconductors? Light emitting diode, LED. You know that part. Light emitting diodes, no, it becomes actually very common. LED TV to your house, like, or illumination in your house, all actually byproduct of compound semiconductor. One reason, you know, compound semiconductor is direct band gap semiconductor, and due to this you are getting something. So it's not about the classified application. more stringent, very special application like high voltage capability, handling capability to common man use. Light emitting diode, lasers, photodetectors, all are made by compound semiconductor. So, but thing is that, okay, detector, I can think like the space detector or defense detector or all these things is very special applications, but still we need it, okay. But what I'm trying to tell you, definitely I do agree that it is not like the CMOS. You cannot make the CMOS out of that. But yes, it has a plenty of application in our normal life. Okay, and that is the one of the reasons that we need to study compound semiconductor. Again, I am telling you, it is a very much compound. It's very this course mainly like a physics oriented course. Like we'll be study the physics behind it, theory behind it more elaborately, because we have started the last semester physics of micro nanoelectronics device, and from there we are going to start. We are going to build the compound semiconductor part. Okay, so that's the things, and yeah, if you are interested on this, there's a lot of research opportunities are there. Okay, I think one of my friend, Dr. Suraj will be giving you idea about photonic integrated circuit. Now, definitely he will explain it more details. I'm not supposed to tell anything, but since I am discussing compound semiconductor, I should tell something about it. And what is that? The thing is that you know that Moore's law is kind of saturated. Actually, I should not tell about Moore's law because I do respect him, but something is happening about the Moore's law. So, our transistor dimension and transistors number of transistor per unit area is not actually increasing now. Okay, there is some problem because already we reach actually quantum region. Okay, now people are thinking, but our people what are thinking now? Quantum computation, spintronics, all these things actually came in market. Okay, now people are thinking of more speed device because our computational demands has increased. People are thinking about genome sequence. Okay, and if you want to have a genome sequence, like even what is the present technology, even if you give this data to a supercomputer, it will take at least 30 to 40 years. So what is required? Required is to increase this computational speed. But it's modern technology, it's not possible. You see the Google investment, you see the IBM investment, you see the Elon Musk investment on it, the computation facility. They are looking not only computing facility, they are also looking photonic integrated circuits. Why? Because instead of transferring an electron from one corner to another corner, you know that effective mass has a lot of variations. It's not traveling with the free electron mass, right? Because when this electron you put into a device in a material, your velocity actually somehow decrease. Now, what's about light? Light is traveling with much more faster speed. And what can handle light? Now, if you are taking a light, so what two things is important, 2 or 3 things. One is you need to have a light source, you need to have a light detector, you need to have a cavity through which light is passing. Light source nowadays either LED, light emitting diode, or laser. Okay, LED and laser is made by compound semiconductor. No other choice. Silicon you cannot use. Detector, photodetectors, mainly silicon are there, but people are preparing compound semiconductor, that I'll see. And cavity may be optical fiber, cavity may be waveguide, or all these kind of things. So what it means? It means the domain is changing. Now people are thinking high-speed device, people are incorporating photonic integrated circuit, and here you need to know all these things. What would be your lasers? What would be your light source? What are the properties of waveguide, and what is the photodetector? The waveguides, the fiber optics things, I'm not going to discuss. That will be part of the Dr. Suraj's lecture, photonic integrated circuits. He will also describe little bit of LED and laser, but I will be taking you in this course in more and more details, like in the theory aspects. Okay, similar detector also I'll take in more theoretical aspects. So this optics is having is taking care of all the modern days electronics, and this electronics actually, what is electronics? Electronics means when you are actually electronics means when you are controlling an electron flow. Okay, and that's what people are somehow related to electronics. So now, if the moment you are controlling a light, which is nothing but photon, so you are saying it is photonics, not electronics, because you are controlling a photon. And photon is higher speed of this electron. But the fundamental thing is that, good thing is that if you want to have an LED, or if you want to have a laser, or if you want to have a photo detector, okay, you need to know, because this device is operating the principle of electronics, not photon. Because the outcome may be the light, means if you have a LED, light emitting diode, when you give a voltage, then the light, then the LED, your LED gives light, right? The LED outcome is voltage, but in outcome is actually light. LED outcome is light, which is nothing but a part of the photonics, but input is actually electronics, because you are giving voltage. And the properties, how it generates light, is a part of the electronics development or electronics region, right? So that is one. Okay. Now, what I am trying to tell you, that you have a three options: photonic integrated circuits, compound semiconductor, and I think that is actually digital VLSI, will be tackled by Dr. Shivarani ma'am. So please, this year is very crucial, because next year you are going to do some project. Choose your subject based on your interest. Okay. If you are going more job oriented things and all these things, so please choose. I should not say anything, but if you are research oriented mind and all these things, so this course may be good. I'm not saying the job oriented people should not take it. So please take a nice decision and come back. Okay. So we'll have a discussion next morning. So I'm not taking the class further, because tomorrow anyhow it's a holiday, and Wednesday, no, I'm not taking. What I'm asking you, requesting you, this week, you please take a decision. This week, you please take a decision that what would be the your electives, 2 out of 3, and then Monday onwards we'll go in course. In this course, we are going to study 3 things. One is properties of compound semiconductor. So this is actually compound semiconductor. First thing that we are going to say, properties. Electronics device or high speed device, or okay, let's write electronics device. Okay. What we'll study? Schottky in great details. In a very details, like MESFET, HEMT. This portion LED, laser, but in great details. Photodetector, PD. Okay. So these properties might have a two parts, so basic introduction or basic properties. Another one is actually fabrication. Look at that. So this fabrication part I'll take care at the end of the semester. Why? Because anyhow you are studying micro nano fabrication technology. Okay. Dr. Sinha will be handling these things. So then you will have a good knowledge on the fabrication. So definitely I want to explore these things. I don't want to repeat all these fabrications, more or less same. What I'll do at the end, I'll tell about some fabrication routes and everything, which will be much faster for me. So within like 4 or 5 lectures, you'll be able to understand about the fabrication. At the end, means after quiz 2. Okay. So that is actually my idea. Okay. But anyhow, so I'll take care everything on next Monday. So please take a wise decision of this. And call your friend, like call the respective, like Shiva ma'am is there, Suraj is there. You please call, you discuss with them, you please attend their courses and try to figure out which would be good for us, for you. Regarding the Shiva, digital VLSI course, I think it's a digital VLSI. Please talk to Shiva ma'am. Okay, so she will guide you what exactly which course and how. Definitely it's an online course, not it's a physical teaching, not like online teaching. There would be, I think it's maybe NPTEL or more, like there will be series of lecture which you need to take it. Okay, there won't be like a faculty interactions like that. So like how the NPTEL is running, so you understand that part. So like that. So please discuss on it. Okay, and then you come back. Okay, so I'm stopping over here. Any question, please? Hello.
No, sir.
Hello.
No, sir. No questions, sir. No, sir.
Okay. Thank you. Books and everything I'll tell you later. Huh?
Okay, sir.
Okay.
Okay.
Thank you. Thank you.